This is Spacetime Series 25, Episode 31, for broadcast on the 14th of March 2022. Coming up on Spacetime, the asteroid Psyche may be less heavy metal and more hard rock, a new way to find planets orbiting other stars, and more breaches by Iran. All that and more coming up on Spacetime.
Welcome to Spacetime with Stuart Gary.
The asteroid 16 Psyche, which NASA intends to visit with a spacecraft in 2026, may be less heavy metal and more hard rock than scientists originally thought. The 225-kilometre wide space rock, which orbits the Sun in the main asteroid belt between Mars and Jupiter, may be far less valuable than many people have thought. Psyche is the largest known so-called M-type asteroid. These are asteroids composed primarily of iron and nickel, so they'd be worth a lot of money to mine, especially when compared to the other type of asteroid that's commonly found, those made from silicate rocks. But as scientists study Psyche in greater and greater detail, it's starting to send back mixed signals about its composition. The problem is, the light it reflects tells scientists that its surface is indeed mostly metal. That's good for mining. And that's led to the idea that Psyche may be the exposed iron core of what was a primordial planetary body, one whose rocky mantle and crust was somehow blasted away, maybe in an ancient collision. The problem is, a report in the journal Geophysical Research Letters, looking at studies which have measured Psyche's mass and density, are telling a very different story. See, the way its gravity is tugging on neighbouring bodies suggests that Psyche is far less dense than what a giant chunk of iron really should be. The study's lead author, Fiona Nichols-Fleming from Brown University, says if Psyche is indeed all metal, it must be incredibly porous, sort of like a giant ball of steel wool with nearly equal parts void space and solid metal. And the fact is, that's very unlikely. So to work out exactly what's going on, Nichols-Fleming and colleagues developed computer simulation models based on known thermal properties of metallic iron in order to estimate how the porosity of a large iron body would evolve over time. The models showed that to remain highly porous, Psyche's internal temperature would need to have cooled below 800 Kelvin very shortly after its formation. See, at temperatures above that, iron would have been so malleable that Psyche's own gravity would have collapsed most of the porous spaces within its bulk. And based on what's already known about the conditions of the early solar system, it's extremely unlikely that a body of Psyche's size could have cooled so quickly. As well as that, any event which would have added porosity to Psyche after its formation, such as a massive impact, would also have heated Psyche back up to above 800 Kelvin. So, any newly induced porosity would have been unlikely to last. Taken together, the results suggest that Psyche probably isn't a porous all-iron body. More likely, it's harbouring a hidden rocky component which is driving its density down. And that raises another interesting question. If Psyche does have a rocky component, why does its surface look so metallic when viewed from Earth? We know from planetary differentiation that the densest part of a planet, the core, is metallic, and lighter rocks and minerals, such as silicates, form in the mantle. Now, there are a few possible explanations, the best of which is probably ferrovolcanism, in other words, volcanoes spewing out iron. It's possible that Psyche is actually a differentiated body with a rocky mantle and an iron core. Widespread ferrovolcanic activity may have brought large amounts of Psyche's core up to the surface, putting a sort of iron coating on top of its rocky mantle. Previous studies have already shown that ferrovolcanism is possible on bodies like Psyche. Whatever the case, scientists will soon get a much clearer picture of this incredible asteroid. Later this year, NASA will launch a new spacecraft called Psyche, which will rendezvous with the asteroid after a 4-year journey into the main asteroid belt. This report from NASA TV.
It's a shame, but living in the city, very rarely do you get to see stars. I feel like I have a new connection to them in a way that I haven't before.
If I'm out in the desert and I look up at the sky, you just see millions and millions of places that we should be going.
It's almost baked into our DNA, the desire to go and explore, right? That's the whole reason why we left the forest and then traveled across oceans just to see what's out there.
I was born in 1969, which is the year we landed on the moon. So I am a space baby.
When I was a kid, there were guys driving cars on the moon. They're driving cars on the moon. That's so cool, right? I want to do that.
All the rocky planets that we know of all have got a metal core in their center. And especially for the Earth, it's the source of our magnetic field. But we don't know a lot about our core. What we've learned about it, we learn indirectly because we can't go there.
It's too hot. The pressure's too high. Our instruments would melt. Can't drill a hole that deep in the Earth or other planets. It turns out we can study a planetary core out in space because there's this one object. It's one object called Psyche.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
It is the only asteroid that we're aware of that is 95% metal or more and is really huge. It's about 200 kilometers across in one axis.
So it's about the size of Massachusetts.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
The first thing that came actually was the theory. Some people from Jet Propulsion Laboratory contacted me and said, we would like to plan a mission that would test your hypotheses.
And that starts you down a road that takes years. So we wrote a proposal to send a NASA spacecraft to visit this big ball of metal. And then about a year ago, Lindy gets a phone call. You win. And then we're all like, oh my God, now we have to do it.
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. So we talked with our mission design and navigation team, and in fact, they were able to come up with what is probably the most optimal trajectory, doing a Mars flyby.
Flies past Mars, gives us a gravity assist, uses that propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
SSL is building the solar electric propulsion chassis. When we do the mechanical, physical integration of each instrument on the spacecraft, we'll work hand in hand with each of the providers to get out to Psyche and do a full discovery mission.
We've figured out a way for many, many people to build something together so complicated, no one person can understand it, but it all has to work together perfectly for decades without fail.
Just the fact that these things work at all is a thrill. It's just a testament to the engineers at JPL and the companies that we collaborate with that they can build these things.
It's exciting for me to be able to be a woman winning and leading a deep space mission. The only previous woman who competed, won, and led a deep space mission was Maria Zuber, who was my friend and mentor at MIT. And so my drive is to make everyone feel welcome and to have every voice heard. We want as many undergraduates as we can. We want to involve as much of the public as we can. We want people to feel like this is their mission.
You get that first picture back, and one of the first things that goes through your mind is, oh, thank God I didn't leave the lens cap on. We will put our pictures out there as soon as they come down. So we'll discover at the same time that the public discovers. We'll be scratching our heads, and it's like, I don't know what's going on. At the same time, everybody else is like, wow, what is that? I don't know, let's figure it out.
I did get to look at Psyche through an optical telescope in my backyard. Some wonderful colleagues brought over their telescope on a fortuitous night. It's a very, very tiny, faint dot. And that made a bunch of us cry to think that we could send something to investigate that speck of light.
We can understand this universe that we live in. We can explore it, we can learn about it, and we can be a part of something which is much bigger than just us or just this planet. We will see new things when we visit a world made of metal.
And in that report from NASA TV, we heard from Psyche principal investigator Lindy Elking-Tanton from Arizona State University, Psyche image instrument lead Jim Bell, also from Arizona State, Psyche deputy project system engineer Tracy Drain, Psyche project systems engineer David Ho, and Psyche project manager Henry Stone, all from NASA's Jet Propulsion Laboratory in Pasadena, California, and Psyche spacecraft chassis program manager Steve Scott from Space Systems Laurel. This is Space Time. Still to come, a new way to find planets orbiting other stars, and more blatant nuclear breaches by Iran. All that and more still to come on Space Time. Astronomers have tantalising new evidence for the existence of hidden exoplanets orbiting distant red dwarf stars. Red dwarfs are the most common stars in the universe. In fact, they make up some 75% of all stars in our own galaxy, the Milky Way. They're also the longest-lived stars, with lifespans estimated to last more than 1 trillion years, far greater than the current age of the universe. The new findings, reported in the journal Nature Astronomy, are based on observations using LOFAR, the world's most powerful low-frequency array radio telescope, which is located in the Netherlands. The authors, led by Dr. Joseph Cullingham from Leiden University in Astron, have been using LOFAR data to search for signs of exoplanets, that is, planets orbiting stars other than the Sun. They discovered radio signals emanating from 19 distant red dwarfs, and 4 of them can be best explained by the existence of planets in orbit around the stars. Previously, astronomers were only able to detect the very nearest stars in the radio sky. Everything else was either interstellar gas or exotic objects like pulsars and black holes. But by using LOFAR, they were able to focus on a wide range of red dwarf stars, which are known to have intense magnetic activity that drives stellar flares, and consequently radio emissions. Problem is, some old magnetically inactive stars also showed up, challenging the conventional hypothesis. And that's where it gets interesting, because these radio signals could be being generated by magnetic reconnection between the stars and unseen orbiting planets, similar to the interaction in our solar system between Jupiter and its volcanic moon Io. Now, the Earth has an aurora, from which the aurora borealis and aurora australis, the northern and southern lights, emanate. And these also emit powerful radio waves generated by interactions between the Earth's magnetic field and the solar wind. But the Jovian aurora are far stronger and are produced in a different way, as Io's volcanoes erupt many kilometres into space. There, this volcanic ejecta fills the space between Io and Jupiter, generating unusually powerful aurora. And the models suggest that the radio emissions being detected by LOFAR are in fact scaled-up versions of the aurora produced by Jupiter and Io, with an exoplanet enveloped in the magnetic field of a star, feeding material into vast currents powering bright aurora, which can be seen light years away. One of the study's authors, Dr. Benjamin Pope from the University of Queensland, says astronomers have long known that the planets in our solar system also emit powerful radio waves as their magnetic fields interact with the solar wind from the Sun. But this is the first time such radio signals have been picked up from planets orbiting stars other than the Sun. Pope says it's an important discovery because it could potentially allow astronomers to find exoplanets throughout the galaxy. But while the authors are sure that the 4 planets are out there orbiting these red dwarfs, they haven't actually been detected by any other means as yet. Follow-up observations using other telescopes, like NASA's Planet Hunting Transit Exoplanet Survey satellite TESS, have already ruled out planets more massive than Earth. But there's nothing to say that a smaller planet wouldn't produce the same radio effect. Pope says while he can't be 100% sure that the 4 stars do indeed have planets, the planet-star interaction hypothesis remains the best explanation we have for what they're seeing.
So what they've done is use LOFAR, the low-frequency array, to discover what we think, and we can't be 100% certain about this, we are fairly certain, is the first evidence of radio emission induced by exoplanets. And so people have been searching for this for decades, and finally, the new powerful capabilities of LOFAR have made this possible for the first time. And this is going to shed light on the habitability and the space weather conditions of planets around M-dwarf stars. And this is also a really great pathfinder of what's going to be possible with the square kilometre array, because LOFAR is just a prototype for the low-frequency arm of the square kilometre array, which will be constructed in Western Australia over the next decade. And I see a very exciting future for all this.
You've looked at a whole bunch of red dwarfs. These are spectral type M stars. They're a lot smaller than our sun, not as hot, but they're very active. These are the most active stars around pretty well.
They flare like crazy. You know, it's very common to see red dwarfs with lots of spots, sometimes with, I suppose this is an astronomy podcast, so some of your audience may be familiar. They have emission of H-alpha, that is the light of ionized hydrogen, and they have these intense flares where they can flare by orders of magnitude in brightness. And so these are very, very active environments. And so it's not terribly surprising to see radio emission from them. In fact, radio emission from flares has been detected many times before. So the crucial thing that we're doing is finding radio emission that's not associated with flares. So that's really where my part of the research came in, is this very exciting circularly polarized radio emission that was detected, circularly polarized just like the auroral emission from Jupiter, could be explained, it may be in some of these cases, as being associated with something like coronal mass ejections occurring on these other stars. On the other hand, what we did is we used TESS, the Transiting Exoplanet Survey Satellite, to get optical follow-up of these sources. What we found in TESS is that some of them are very, very flary sorts of M-dwarfs. Common or garden variety radio emission from flares was perfectly plausible in some of these cases, but some of them were dead quiet. Some of them had completely flat light curves in TESS. They didn't show any significant variability. They didn't show any significant flares. They must have had very long rotation periods. These same stars show very minimal X-rays and very minimal H-alpha emission and other signatures of activity like that. And so it's very surprising to find such strong radio emission with no other reasons for activity-driven emission to be there. The conclusion is that for at least these stars, which are very, very inactive, and nevertheless show this very strong radio emission, the emission, which is highly circularly polarized, and it seems to vary on-off, but it doesn't vary smoothly, up and down all the time. So this is something where we think we're catching a beam sometimes or not at other times. This is actually very consistent with the behavior of, say, Jupiter, which gives exactly this beamed, circularly polarized, steady emission. And for what theoretical models predict, what would happen around M-dwarf stars that are magnetically connected to their planets. So what we actually think is happening is it's not auroral emission from Jupiter per se, but at astronomical distances, but it's actually that Jupiter and Io are magnetically connected. And this is actually what drives Jupiter's aurora, is this dynamo formed by Io whipping through Jupiter's magnetic field. Actually, what we think is happening is it's like having a scaled-up version of Jupiter Io. You've got a small planet in a close orbit whipping around the M-dwarf, where the M-dwarf is like a scaled-up version of Jupiter and the planet a scaled-up version of Io. And so we think this kind of radio emission is very consistent with models like that, and this would be the first evidence to be observed of planets that are directly connected to their stars via magnetic field.
And you found four of these?
Four of these good candidates where there's no evidence activity, and they seem to be nevertheless radio bright with steady circularly polarized radiation. And we're very, very excited. Previously, one of these has been published, GJ1151, but now we've got a lot more data with more sources and, crucially, this optical follow-up. And so we find it hard to make any explanation other than that this is emission from exoplanets connected to the stars. On the other hand, the big caveat there is we haven't been able to detect the planet. I've burned a lot of telescope time, and so have other people. Sivarath Mahadavan on the Habitable Zone Planet Finder, and Perdue et al. On the Carmenes Observatory in Spain. We've all burned a bunch of telescope time trying to find such a planet using radial velocity maps. And nevertheless, we've only been able to put upper limit on any planets around these stars. GJ1151, we can rule out planets that are more massive than about 1.2 Earth masses, but that's not extraordinarily massive. The thing is, we can actually use a fairly sensitive limit, but it's perfectly consistent. This radio emission is perfectly consistent with being produced by an Earth mass planet, and we wouldn't be able to see that. So we're in this difficult position where we've got every reason to believe that there's a planet there, except for direct evidence of a planet. So we just got to do more work. We know that they don't transit, and we know that we don't have any huge RB signals, at least on the ones that we've been able to observe. But the other details of these planets are sort of unclear, because really the crucial actor in producing this aurora is really the star and its magnetic field and its powerful stellar wind. The planet, it's a little bit harder to find out about.
There's always this caveat with red dwarfs is these aren't the sort of planets you could hope to expect to find life existing.
Au contraire. Really, on the contrary, people, sort of a cottage industry around in searching for biosignatures around M dwarfs.
This is because the halo shape of the burst coming from the star leaves the planet in a clear zone.
Well, there's a lot of detail still to be worked out about kind of space weather environment of M dwarfs. And I think our discovery, if it holds up and our explanation is broadly correct, our discovery is really the end of the beginning of trying to do this rather than anything else. Our resolution to the question is it's been very hard for a long time to understand what are the stellar winds of M dwarfs, how do they impinge on exoplanets, and how do these affect planetary atmospheres? Because for a long time, there's been a sort of an argument that runs along these sorts of lines about why M dwarfs are important. They're the most common kind of star in the universe. They live for 1 trillion years. They all have planets. The first approximation that planets around M dwarfs are extraordinarily common. And because they're so faint, planets on short orbits are actually in temperate, some would say habitable zones where they have Earth-like temperatures. So it all sort of shapes up that these are easy to observe, they're plentiful, they live for a long time, and they all have planets in their short orbits that might be habitable. And so there's been a bit of a cottage industry in more than cottage. It's one of the driving forces behind the launch of, say, James Webb Space Telescope is to look for biosignatures on planets around M dwarfs. But here's the trouble. M dwarfs, as you said earlier, they're very, very active. They're very intensely magnetic. The reason is that they're fully convective all the way throughout. So they've got this intense boiling motion that goes all the way to the core, and this drives a very powerful kind of magnetic dynamo, which is strong and not as stable as we have in, say, the sun, which has got this stable radiative core and only a convective envelope. And so one of the consequences of this is that they have flares, they have intense UV radiation. And so people have often thought, well, M dwarfs might be too good to be true. This argument that M dwarf planets might be habitable is often made, but it might be the case that while they're very temperate, they nevertheless have very harsh radiation environment. And so this is really work that sort of probes these effects and is able to actually begin to quantify what kind of radiation environment these M dwarfs are receiving.
But I guess the other side of that is the latest research suggests that although they do flare, the flares aren't around the equatorial region of the star. They're actually coming from more polar regions, which, if that is proven through a large number of red dwarfs, that would change the picture somewhat.
Yeah, it would. No, I'm familiar with the research you mean. I sort of a little hard to know at this stage. We're only able to do this.
The paper's only a month old or so.
So a few rare cases, people have been able to, if not pin down, at least estimate the latitude at which these flares are occurring. And it does seem to be the case that some of these flares are occurring at high latitude near the poles. And so maybe that is good news, at least on the flare front of these planets. But what we're showing in this research is that planets can be so close to the star that they're inside what's called an Alfvén surface, after Hannes Alfvén, the plasma theorist, where magnetic effects are more important than fluid flow. And when you work through all the physics, this means there's a qualitative difference between what happens to a planet that's inside of this, they sometimes call it the Alfvén sphere, this region close to the star that's magnetically connected to the star, and this region outside of this is very close to the star. A planet will be directly magnetically connected to the magnetic field lines of the star, whereas we, on the Earth, are actually far enough away from the sun, which is gentle enough in its magnetic field, that we have a separate magnetosphere which is delineated by this shock that protects us from the solar wind. Solar wind streams around the Earth's magnetosphere, but only a small fraction actually enters the Earth's magnetosphere and impinges upon the Earth. And so this causes beautiful aurorae on the Earth. It's all very nice if you go and visit Iceland, or if you're lucky, Tasmania or something, and you can see the northern and southern lights.
In fact, at time of recording, there's one happening right now.
Yes. I would love to be somewhere other than Queensland right now, except for all the beautiful things we have in Queensland. But I'd love to be able to see somewhere at high latitudes where you could actually see the aurora that I think is starting to pick up, is my understanding. But it'd be very different on one of these M dwarfs. You'd think all aurora all the time, all the way down to the equator on one of these planets, because you get magnetic field lines directly connecting the star to the planet, just bucketing solar wind directly down onto the planet's atmosphere. And, well, it might be very pretty for a short while, but that kind of flux of particles would actually strip away the atmosphere on reasonably short geological timescales, is my understanding. And so we actually might end up that these planets are stripped bare of atmospheres, that they're sort of lifeless rocks, or at least very challenging rocks that are bathed in high-energy charged particles. And this is sort of something that's not inconsistent with understanding of, say, such famous systems as TRAPPIST-1, where astronomers have continued to struggle to detect any atmosphere even around supposedly habitable planets in the middle of that system. And so it might be the case that their Chile-Grapho calls it a threatening radiation environment, where they're actually in this subalphenic zone, inside this alphane sphere where they might be connected to the star, might have stripped away these atmospheres long ago. And so it's not that we can conclusively prove that this is the case, but the signal that we've observed is exactly what theorists like Robert Cavan at Trinity College Dublin have actually simulated the radio signal from one of these scenarios would actually look like. And so what we want to do is to continue to follow these up, to look for periodicity, to look for changes in the radio spectrum that are consistent with simulations like Grapho or Cavan and make. And then we'd be able to make an even stronger argument. This is sort of an exoplanet connected to the star, driving this kind of auroral emission side.
These 19 red dwarfs that you guys were looking at, are they all over the sky, or they're in one area, or what?
So they're in an area of the northern sky that was intensively observed by LOFAR in the LOFAR 2-meter sky survey. And so this is a major project of LOFAR, looking at a wide area of the northern sky, and they've only processed and completed sort of a fraction of lots so far, but they've done some amazing work already. And so as they continue, I do expect that we'll find more of these.
Lots more to come.
You said it better than me.
That's Dr. Benjamin Pope from the University of Queensland. And this is Space Time. Still to come, more blatant nuclear breaches by Iran, and North Korea resumes its missile tests. All that and more still to come on Space Time. In yet another flagrant breach of its nuclear non-proliferation treaty agreements, Iran has test-fired a nuclear-capable Qased missile, this one placing a small cubesat-sized spacecraft called Noor-2 into orbit. The Islamic Revolutionary Guard describes the Noor-2 as a reconnaissance satellite. Washington described the launch as a clear violation of United Nations 2015 Security Council Resolution 2231, which calls upon Iran not to develop any ballistic missile capable of carrying a thermonuclear warhead. The Islamic Revolutionary Guard says the missile was launched from a site 300 kilometers east of Tehran. The Qased, which is Persian for messenger, first stage uses a Ghidar medium-range ballistic missile, and testing this missile undoubtedly was the real reason for the launch. The missile, which has a diameter of 1.25 meters, is based on the North Korean Nodong-1 ballistic missile, burning unsymmetrical dimethylhydrazine and dinitrogen tetroxide for 103 seconds. What Tehran's simply done is place a 1-meter diameter second stage based on a Salman anti-ballistic missile system, which uses a solid fuel propellant burning for 60 seconds on top of the first stage, and call it a space rocket instead of a ballistic missile. The missile's third stage is nothing more than a solid fuel apogee kick motor with a burn time of 40 seconds. The thing is, the missile's designed to be launched from a mobile transporter erector. Exactly the sort of thing Tehran would use if they were launching a nuclear missile against Europe or Israel. It's important to also note that the flight was timed to coincide with the latest round of Iranian nuclear weapons talks between Washington and Tehran, which are taking place in Vienna. The latest launch follows a test of another Iranian missile, the Seymour, in late December. They're simply the latest in a growing list of broken agreements by the Islamic Republic, which have included refusing access to International Atomic Energy Agency weapons inspectors or disclosing the location of key nuclear weapons components in Iran's possession. The International Atomic Energy Agency says Iran started using advanced centrifuges designed to enrich uranium in high volumes. The Islamic Republic's stockpile of enriched uranium now stands at over 3,241 kilograms. That's more than 16 times the limit it agreed to in the 2015 Vienna deal. Just a year ago, in February 2021, the United Nations nuclear watchdog found that Iran had started producing uranium metal, a material used only in nuclear weapons. And in April 2021, both the German and Swedish intelligence agencies issued warnings of growing efforts by Iran to obtain nuclear weapons technology. For its part, the oil-rich nation insists its nuclear program is for peaceful power generation only. This is Space Time. Still to come, North Korea resumes its own missile tests. And later in the science report, discovery of the wreckage of polar explorer Ernest Shackleton's ship Endurance. All that and more still to come on Space Time. North Korea has resumed its long-range ballistic missile tests in line with similar tests being undertaken by its close ally Iran. Pyongyang claims the latest tests have involved a new reconnaissance satellite. It follows a month-long unexplained break in missile testing during February. Analysts speculate that just as Moscow delayed its invasion of Ukraine under orders from Beijing so as not to take attention away from China's Winter Olympics, North Korea was ordered to pause its missile tests for the same reason. And with the Games now over, both Moscow and Pyongyang have been let off the leash. North Korea's latest test is believed to have involved a solid fuel-powered Pakuksong-2 intermediate-range ballistic missile. The 9-metre-long missile is designed to be launched in minutes from a mobile transport erector. Analysts describe it as being more stable, more efficient, and harder to detect than North Korea's previous liquid-fueled designs. Pakuksong-2 is thought to be an enlarged two-stage development of the original Pakuksong-1 submarine-launched ballistic missile. It's canister-launched from an enclosed transport container. It uses a cold launching system, which involves using compressed gas to literally blow the missile out of the launch tube, and then the engine ignites in mid-flight. Over recent months, North Korea has undertaken multiple tests, including its medium-range Hwasong-12 ballistic missile and a reportedly new hypersonic missile design, which was tested in September last year. Meanwhile, there are growing reports of renewed activity at Pyongyang's Punggye-ri nuclear weapons test site. North Korea carried out 6 nuclear tests at the facility between 2006 and 2017. But it was closed in 2018 when North Korea declared a self-imposed moratorium on nuclear weapons testing. However, the hermit nation's leader, Kim Jong-un, now says he no longer feels bound by the moratorium, with denuclearization talks stalling in 2019. This is Space Time. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that by 2040, we could see the increased variability of rain patterns associated with La Niña and El Niño events, regardless of which climate emission scenarios we follow. The findings, reported in the journal Nature Climate Change, looked at how these climatic patterns, known as the El Niño Southern Oscillation, will change under different emission projections. Scientists found that changes in rainfall variability will occur around 2040, about 30 years earlier than changes in sea surface temperatures, regardless of which emission path humanity follows. Rainfall variability in the tropical Pacific caused by El Niño Southern Oscillation patterns is the major driver of climatic variability in Australia. The authors say that this reinforces the rapidly emerging risks of La Niña and El Niño-related climatic extremes, regardless of mitigation action. Israeli and Australian scientists have developed a single DNA test that can screen a patient's genome for more than 50 different genetic neurological and neuromuscular diseases, including Huntington's disease, muscular dystrophies, and Fragile X syndrome. The new test, reported in the journal Science Advances, avoids a diagnostic odyssey for patients which can take decades. Researchers have already been able to confirm the accuracy of the diagnostic process and are now working on ways of making it available in pathology labs. They expect it to become a standard test in most labs within 5 years. Well, after more than a century in the frigid waters of the Antarctic, marine archaeologists have discovered the wreckage of polar explorer Ernest Shackleton's ship Endurance. The 144-foot-long three-masted wooden sailing ship was lost in November 1915 in the ice-covered Weddell Sea after being crushed by Antarctic sea ice during Shackleton's failed attempt to make the first land crossing of Antarctica. The wreckage was found in 3 kilometres of water by members of the Falklands Maritime Heritage Trust using remotely operated submersibles, or ROVs. The vision shows the vessel upright, well proud of the seabed, and in remarkably good condition, with its name clearly visible on the stern. Despite being stranded on the ice, Endurance's 28-man crew made it back home alive after trekking across the sea ice and then setting sail in 3 lifeboats to the uninhabited Elfin Island. From there, Shackleton and a handful of crew rowed 1,300 kilometres to a whaling station at South Georgia Island to get help to rescue the others. It's regarded as one of the greatest survival stories in human history. A senior research project about the correlation between religion and the paranormal has found that religious people tend to watch more ghost hunting stories than agnostic people, but the difference isn't significant. Tim Mendham from Australian Skeptics says the findings disprove the author's original hypothesis that religious people were less likely to watch ghost hunting shows, while those who identified as agnostic would be more likely.
There is an interesting correlation which doesn't exist, and this particular paper that was published in a Christian online publication says as much. It says, in fact, it's actually conclusions are very confusing. Christian people actually watch slightly more often these ghost hunting shows than agnostic people, but not a significant enough amount that we could conclusively say they watched more. So they say they watch more, but not enough to say they watch
only
more.
Itsy bitsy bit more.
And then people who, when they say religion and interest in ghost hunting shows do not correlate.
So the religious people watch the boring ones.
Yeah, well, they say a discovery was that spiritual people seem to be much less interested in ghost hunting shows. So there is a relationship between religion and ghost hunting shows that's just negative. Sometimes you look at studies that are being done and you think, really? They're quite pathetic, unfortunately, whether they're done by scientists or amateurs or whatever. You look at some of these things that are published as papers, whether they're peer-reviewed papers or not. This was a paper called A Correlation Between Ghost Hunting Shows and Religion, ? In which they say there's none, but there isn't. And it's the classic one of hedging its bets, and also, as happens with a lot of these papers, is that, all research required, so they give me another grant.
Oh, but that's a standard one in all science, not just...
That's right.
All science, the more statistics you can gather, the more you can confirm a hypothesis. That's what science is all about.
Well,
the more evidence
this is going in with the hypothesis.
That's true for all sciences, but I guess when you're dealing with ghost hunting and things like that, you really need that extra money to try and justify statistics that don't exist.
Well, this is actually just ghost hunting shows they're watching. It's not even actually necessarily finding ghosts. It's the sort of people who are interested. You talk about statistics, and this project was based on 100 anonymous surveys and 6 in-depth interviews. But then they had to drop out a number of the anonymous surveys because they didn't have enough of a particular religious group, Judaism and Islam. So they basically come down to some Christian groups only. And then they kept dropping out numbers. So the actual numbers involved in these surveys is pathetically small. So even basing any conclusion on that small number of people is dodgy, especially when they come out with there's no result. It's the sort of thing you look at and, quite frankly, you throw away pretty quickly. Most religions have ghosts. I mean, Islam has jinns and things like that, which are sort of ghosts or spirits. But the Pentecostal religions and that sort of stuff, which have a predisposition to believing in the afterlife for a start, therefore they might show a greater interest in ghost hunting shows to prove their belief in the afterlife and that sort of stuff. But apparently they do, but they don't, according to this survey of less than 100 people.
That's Tim Mendham from Australian Skeptics. And that's the show for now. Spacetime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from spacetimewithstuartgary.com. Spacetime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the Spacetime store for a range of promotional merchandising goodies, or by becoming a Spacetime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more Spacetime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our Spacetime YouTube channel, and on Facebook, just go to facebook.com/Spacetime with Stuart Gary. And Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. This has been another quality podcast production from Bytes.com.